Hello everyone. I would like to speak on model for terahertz communication. Uh, my content will cover history. Where does this terahertz actually operate? And then I'll be introducing it basically. Then the parameters which is related to the terahertz communication, applications of terahertz communication, future research directions, terahertz channel, terahertz uses, and finally I will be concluding with my references. Okay, so now dating back to the history, the first occurrence of the term terahertz in these transactions is attributed to Fleming in 1974, where the term was used to describe the special line frequency coverage of a Michelson interferometer. And a year earlier, Kerichman applied terahertz to the frequency coverage of point contact diode detectors in an IEEE MTTS Conference Digest paper. Ashley and Palka used the designation to refer to the resonant frequency of a water laser in the same digest. Okay, so spectroscopists had much earlier coined the term for emission uh, frequencies that fell below the far infrared. Today, terahertz is broadly applied to submillimeter wave energy that fills the wavelength range between 1000 to 100 meters. Now, where does this terahertz actually operate? So, as we can see in this slide, that um, from 4G to 5G, the evolution has been from 10 to 100 Mbps to 100 Mbps to 10 Gbps in case of 5G. Okay, it's like the sub 6 gigahertz bands were in the range of 3.4 to 3.6 gigahertz wave. It was from 24 to 100 gigahertz bands, and sub terahertz. It was from 100 to, this was basically, yeah, sub terahertz. It was basically from 100 to 300 gigahertz bands. So wave today, it is basically from 24 to 100 gigahertz. Began deployment in 5G, 100 to 400 gigahertz typical bandwidth, and peak rates, which is greater than 1 Gbps. And beyond 100 gigahertz, the sub terahertz bands is from 100 to 300 gigahertz, and terahertz is basically from 300 gigahertz to 3 terahertz. It is largely unexplored, and this is a completely new field. So the research is going on so that maximum exploration can be done and we can use it, because there is now, as we all know, there is a shortage in the spectrum, and we want to explore the other areas and other aspects so that we have an advantage and we are able to use things efficiently, which is already present. Okay, so now coming to the introduction, terahertz ranges from 300 gigahertz to the 2-3 terahertz, but generally the term is now being used by the industry to mean frequencies above 100 gigahertz. And the motivation for these bands is that there is a vast amount of bandwidth available in these frequencies, and vast new applications such as imaging, spectroscopy, and wireless replacement which can occur. An exponential growth of the data traffic in wireless communication system led to the use of terahertz frequency band. This was thought of to support ultra broadband to support beyond the 5G level. So basically, we know that our current generation or the current time is basically heading towards 6G. So that means what? We need more bandwidth, more data rate. So this is what terahertz communication is aiming for, so that they are able to cover more of data rate. Okay, so this bridges the gap between the wave and optical frequency ranges. Okay, so then terahertz radiation basically falls in between infrared radiation and microwave radiation in the electromagnetic spectrum, and it shares some properties with each of this. So, like infrared and microwave radiation, terahertz radiation travel in the line of sight and is non-ionizing. Like microwave radiation, terahertz radiation can penetrate a wide variety of non-conducting materials. Terahertz radiation can pass through clothing, paper, cardboard, wood, masonry, plastic, and ceramics. The penetration depth is typically less than that of microwave radiation. So now coming to the block diagram of terahertz communication, we can see over here the terahertz source. It has got multi-level terahertz wave modulator, terahertz detector, digital demodulator, and then we can see the output data. And that we control is we control is basically that is controlled by the digital ASK modulator. Okay, so now coming to the parameters related to terahertz communication. At 1 terahertz, the radiated signal has the following characteristics. So what are those characteristics? We see that the wavelength is 300 micrometer in free space and period is 1 picoseconds and photon energy is 4.14 MeV. Now I would be explaining terahertz channel over here. The key requirement for accurate terahertz channel sounding are high dynamic range within a narrow frequency range while maintaining wide tunability, and fast detection to capture real-time dynamics, and a long enough measurement window to capture power delay profiles. More generally, long measurement windows and real-time dynamics are conflicting requirements that can only be met with a compromise. Okay, so now coming to the applications of terahertz communication, we have the terahertz nano applications. On a nano as in like it's very small in the ranges of nanometer. We know, so like what, 10 to the power minus 9 meters. So that's the scale. We can see that it's a very small unit. With the advent of the Internet of Nano Things, the interconnection of various objects, sensors, as well as devices result in ubiquitous networks tailored not only for device-to-device communication but also for extracting data from areas which is hard to access. Terahertz microscale application. So now terahertz wireless communication promises during applications that meet consumers' demand of higher data rates, especially at the microscale. Wireless local area networks and wireless personal area networks form the basis of such applications, which include high definition television and home distribution, wireless displays, seamless transfer of files, and terahertz access points in the areas with human congestion. And then terahertz macro scale applications. On a macro scale, terahertz wireless communication facilitates potential outdoor applications which ranges from few meters up to kilometers. For instance, wireless backhauling, front hauling is one of the envisioned applications for the standard 100 Gbps transmission solutions. In terms of backhauling, wireless point-to-point links are widely applied for transmission of information to the base station of macro cells, especially in those points where optic fiber is not available. Okay, so now coming to the future research directions, we can see terahertz ultramassive MIMO. The terahertz frequency band is considered a key enabler in satisfying the continuously expanding bands of higher data rates. Yet, despite the huge bandwidth it provides, the band suffers from high atmospheric losses. Therefore, high gain directional antennas are utilized in order to invoke communication over distances exceeding a few meters. Especially in the terahertz band, antennas become smaller and more elements can be installed in the same footprint. Terahertz communications for mobile headnets. So, as the demands of communication services are developing in the direction of multiple users, large capacity and high speed mobile heterogeneous networks which combine various access network technologies have become an imminent trend. As such, applying the terahertz technology to headnets is a promising way to improve the transmission rate as well as capacity and achieve a throughput at the level of terabits per second. Terahertz 3D forming technology. One of the anticipated key enablers of terahertz wireless system is 3D MIMO technology. In fact, real-world channels emphasize 3D characteristics, leaving 2D MIMO techniques suboptimum. 3D beamforming emerges as a solution to allow the construction of directional beams, extend the communication range as well as lower the interference level. So such technology holds a lot of promise to mitigate the unavoidable path loss experienced by the terahertz channel. So now coming to the advantages of terahertz frequency. So now why will we basically go for this terahertz frequency? So let's see. Ultra high bandwidth. Terahertz communication have the potential for increased bandwidth capacity compared to microwave systems. Unregulated frequencies. Frequencies above 300 gigahertz are currently unallocated by the federal frequency and offers very high bandwidth. Directional beam. Terahertz communication are inherently more directional than microwave or millimeter links since terahertz waves have less free space diffraction. The link budget analysis suggested at the same antenna aperture with the microwave transmission for the 350 GHz require a large gain per antenna, which requires terahertz emission to be highly directional, and therefore a line of sight detection is required. So high security. Terahertz communication can be implemented as a secure communication link. So terahertz can support ultra high bandwidth spectrum systems, which can enable secure communication, large capacity networks, and protection against channel jamming attacks. Okay, so now coming to terahertz uses. Terahertz spectroscopy has number of applications, run from detecting defects in table coating, then to product inspection as in industry, spectroscopy as in chemistry and astronomy, material characterization as in physics we can see, weapons concealed under clothing, airports, and detection of cancers and caries. Okay, so these were my references. I hope this topic will be beneficial to you and you have gained some knowledge and idea from my slides. Thank you.